Chad came this morning and asked me about problem 4. Is that the one you wanted to look at? Okay. So problem 4, we have basically this for a potential. And so drawing a diagram of that, and of course we can't make a 3-dimensional picture, so we draw it 2-dimensional. How do we know what?
How do we know that energy has to be less than V0? Because it's a scalar.
Well, notice I drew 2 options here.
Yeah.
We have the terms bound and unbound. If the energy is less than V0, then it's bound. And if energy is greater than V0, then it's unbound.
But something like the energy is going to be negative for a hydrogen atom. So
for a hydrogen atom, yes, but for this case, no. Remember, for the hydrogen atom, our potential energy V was negative. Here, our potential energy was 0 or positive.
Well,
and so total...
Like it says V0, but V0 could include a negative sign. How do we know that?
While technically that's right, you know it's not, because otherwise our picture would have looked like this. And there is no bound state.
So there has to be a well for it to be.
So, yeah, there has to be a well for it to be a bound state. A well of some type. It doesn't have to be a square well, of course. And so this is what it looks like. And so we know that the energy is positive. Because, I mean, when I went through it with Chad this morning, I had to think through these things too, as well.
That's what comes back.
So at this point, we can look at page 141 of the textbook, where it essentially goes through this problem, except it, doesn't do our problem, God forbid. So we're going to have, and this is the thing I forgot, so I'm going to mention now. We define U is equal to RR, where R, capital R, is the solution to the actual Schrodinger equation. So that would be the radial wave function, I guess I should put. And this is a really important thing. I got to 5 minutes before I had to leave, and I was stuck, and I'm like, what? And so I peeked at my notes, and this was the thing I had forgotten. So what you're going to do with this problem is, well, you start with your Schrodinger equation, right? And after this definition of U, our Schrodinger equation became d second U, our radial, whoops, not equals plus. And I don't have this memorized. That's why I'm reading it from the book. If you do have this memorized, well, you have too much time in your hands. So we have this Schrodinger equation for U. And then the problem simplifies things by saying, somehow that's not the red pen, L equals 0. So if L equals 0, this whole thing is just going to 0.
Shouldn't there be a negative h bar squared over 2m in front of the d squared and d r squared?
Yes, there should. See, I started by copying equation 441, and then I came back and realized that wasn't the right one. Yes, there should. Yeah. So adding, and I'll add a couple pages just because God only knows how many pages I'm going to use here. 3. So if we take that, so rewriting that's rewriting it with the L equals 0. And so we can simplify this further. Like that. So I subtracted the u from both sides, and then I divided by minus h bar squared over 2m. So now our solution is going to have a form that we know. We know the solution has the form u is equal to e to the br. And so that means u, second derivative of u, is b squared e to the br. And we have an equation that says b squared u equals v minus e 2m over h bar squared u. So there's a very general solution. And that would be a solution inside or out as long as v is constant, which it is in this problem. So now we have to look at our two regions. So region 1, r is less than a. Then I'm going to have v equals 0, right? And so b is equal to plus or minus the square root of minus e 2m over h bar squared. Since e has to be positive here, then that means this is going to be imaginary. So define k as the square root of 2m e over h bar squared, and have b is equal to plus or minus ik. So that means u must equal a, and let's just put cosine and sine for the, well, there's technically based on what I did, which is equivalent to c cosine, oh, I forgot the r's, cosine kr plus d sine of kr. Now, as I said, the thing I overlooked when I was working with Chad this morning, this is u. This is not our wave function. It's our wave function related to, well, it's related to our wave function. So to get our wave function, r is going to be equal to this u divided by r, since u is defined as radius times the r function, the radial function. So if I apply that, r is equal to c over r cosine of kr plus d over r sine of kr. Now we have some restrictions on our wave functions. Our wave functions, well, tell me, what are restrictions on our wave functions? Perfect. Must be continuous and normalizable. So we look at this. Now, this was in the region for r less than a. And of course, r can't be less than 0. So r is less than or equal to, or r is greater than or equal to 0, and less than or equal to a, technically. I've been loose with my less than signs versus less than or equal. So we take this and we have the limits. Now, sine and cosine are both continuous. Sine over r and cosine, or sine kr over r, cosine kr over r, they're continuous except one location. They approaches infinity at 0. So if we look at this, what is cosine of 0? What is sine of 0? So if I have c times 1 over 0, what is that equal to? Infinity or undefined. So the only way that I can use this is c must be equal to 0, or else I'm going to have something that is not normalizable. Now we look at the other one. If that one's also the same problem, we're in trouble. So what is sine of 0 over 0? Yeah, it's indeterminate. You have to use L'Hopital's rule. So if we take that, the limit as r approaches 0 of d sine of kr over r is equal to the limit as r approaches 0 of the derivative of the top, which is dk cosine of kr, over the derivative of the bottom, which is just 1. And so that's going to be dk times 1 over 1. So dk. That's not a problem. It was indeterminate. We used L'Hopital's rule, and we say, yeah, it's fine. Which is good, because otherwise problem over. I mean, you might have said, hey, it would have been even better if problem was over. So now we have our radial function inside is equal to d over r sine of kr. So we have the inside function. Now we look at the outside function. So outside, r is greater than a. Then we have the value of v0 is greater than e for it to be bound. And so our solution is going to be just going back to what we had before. We had b equaled plus or minus the square root of v minus e 2m over h bar squared. Well, now v minus e is positive, so define kappa as square root of v0 minus e 2m over h bar squared, and b is equal to just plus or minus kappa. That's a kappa. I know it looks like an I because my brain was going the wrong direction. That looks like a K. So that means our solution outside is u equals, I'm going to use a and b again because I abandoned those. A e to the kappa r plus b e to the minus kappa r. Once again, Chad told us that it has to be normalizable and continuous. This is going to be continuous in all r's from a to infinity, but as R approaches, actually, I should probably be more careful. Capital R outside is equal to U over R is equal to. It's not going to matter for what I'm doing, but I should just be more careful. So now we have our requirement that as R approaches infinity, R out has to approach 0. And so if you look at those terms, one of them does, one does not. Which one does not? So A has to be 0 because e to the kappa R over R is approaching infinity as R approaches infinity. And somebody might say, but isn't that infinity over infinity? And they would be absolutely right. And how would you resolve that? Use L'Hopital's rule again. And just like before, we're going to bring down a kappa on top. It'll be kappa times infinity. Well, A kappa times infinity over 1. That's still infinite. So A has to be 0. So that means our out is equal to B over R e to the minus kappa R. So we have our R out and we have our R in. And then we have our boundary conditions. What's our boundary conditions?
That they must equal each other at R equals A.
And
And that the wave functions or the derivative must be.
yes, I say wave function being continuous is what you said. So we do those derivatives. So I know I'm just using a whole lot of class time for your homework, but I can't stop. So I have d sine of Ka over A equals B e to the minus kappa A over A. That's the first boundary condition. And my second boundary condition, just take the derivatives. Now the derivatives are not as simple because I have a quotient, if you will. So yeah, what's the derivative of d sine Ka over, or Kr over R? That should be correct, right? I did the product rule and then put in the A's immediately. In your homework, you should show the intermediate step. And so we have two equations, and we have D, B, K, and kappa as unknowns here. So we're obviously not going to solve everything from these, but we'll see what we can solve. So what I'm going to do is just find B in terms of D. First thing to do is probably get rid of an A everywhere. And then replace D with KB e to the minus kappa A over sine Ka times cosine Ka minus d sine Ka over A. Poop. Gotta replace the B. I should have just divided. Wouldn't that be quicker? Yes, it would be quicker to divide. So if I divide the left side by this and the right side by this, I will have K sine or K cosine all signs correct? So I should have K, K cotangent of Ka equals minus kappa plus 2 over A. Now this function here is one that both the K and the kappa depend on E. And so now I'm not guaranteeing I have all my signs correct here. I think I do, but I did it correctly. So now you have an equation that has E a couple different places to try to solve. And I will leave that to you from there on. Remember transcendental equation, how we did it before? I like to do it graphically, but I then use a spreadsheet and I can narrow down to get more precisely what the values are. Because I believe that's what we have. Well, that's what I have here if I did it right as a transcendental equation.
So we should just follow the same procedure
from the last time. Yeah. Okay, so that's as far as I'm going to take it because, yeah, it's assuming I made no mistakes. I'm sure you're going to get a transcendental equation. Assuming I made no mistakes. Now you've got some work to do. Okay. Picking up where we left off last class period for the second half of today's class, we had come to finally a quantization relation. That is that the energy was some E1 I wrote here over n squared. And what is that E1? It's this right here. And for the hydrogen atom, what is this M? It's a mass. I think it's a mass. Yeah, it's a mass. What's it the mass of? The electron. It's the mass of the electron. Now,
that energy equation is just not ringing any bells for me right now. When did we derive that?
That was the last thing we had done in class yesterday.
Right, but we still have. Okay, so ME squared over 2 pi epsilon. So that stuff is from the potential energy.
Okay, so backing up, we had our restriction on J. We said J has to terminate, and we set N to be related to the termination J max plus L plus 1 is equal to N. And so that gave us a relationship between that N term and rho 0. And then, we have to go all the way back to the Schrodinger equation to where we had defined, to get to where, this is where we had defined row 0 based on, all these pages. Okay, and that goes back another lecture, and I don't have that one loaded up. But we started with our Schrodinger equation that was minus h bar squared over 2m d second d r squared, blah, 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 blah. That's where the m came from. And that was the mass of the electron is what we said. Now, you said of the atom or the nucleus or something like that. And the fact is, one of the corrections we are eventually going to make is that it's not really an electron orbiting a stationary nucleus. Just like the Earth is not really orbiting a stationary sun. What's happening in the Earth? The sun is moving a little bit too. So the Earth is doing big circles in its orbit. The sun is doing small circles in its orbit. Why is the sun doing small circles? Because it's much more massive than the Earth. We have the same relationship with an atom. The electron is far less massive than the nucleus, so the nucleus doesn't move very much. And so we started this problem treating it, I didn't even say this, we just treated it as if the nucleus was fixed and the electron was orbiting the nucleus. So one of the corrections we're going to make after we get this all straightened out is to say, okay, really the nucleus can move too. And we're going to end up replacing that mass with what we call the reduced mass, which is the product of the mass of the nucleus times the mass of an electron divided by the sum of them. But for now, okay, where are we? Where are we? Okay, yeah, we were on this slide. But for now, we're using m as the mass of the electron. Like I said, later on, we'll use mu, which is mass of the electron times mass of the nucleus over mass of the electron plus mass of the nucleus. But if mass of the nucleus is way, way bigger than mass of the electron, then the denominator is approximately the mass of the nucleus, and you cancel it and you have just mass of electron. So the difference is pretty small between reality and what we have right there. This whole thing then is calculated, and that's what gives us minus 13.6 electron volts. So if you actually put in the mass of an electron, put in Planck's constant, put in the charge of an electron, put in the value for the permittivity of free space, you'll get minus 13.6 electron volts when you convert units. So we have what I consider a great result. We now have an equation that shows us quantized energies for electrons in a hydrogen atom. As a chemist, that's like 80% of what you care about, right? The other part is now what kind of orbital is it? Is it s orbital, p orbital, and that kind of thing. And that came from what we've already done with the spherical harmonics. So fundamentally, we had now derived everything that you really care about as a chemist until you get to really high levels. But we're going to continue to go on and understand it better, understand about electron spin and how that plays into this. Get past these 3 pages. Now, returning to that definition of n. N was telling us about the termination, but n wasn't the terminal, it didn't tell us the number of terms in the polynomial. J max tells us the number of terms in the polynomial. So in theory, you could have when I say number of terms in the polynomial, I should have said the highest power in the polynomial. There is a difference. So what's the lowest power you could have in a polynomial? 0. Yeah, you could just have a constant. And so if J is 0, then you have N is equal to L plus 1. We already established that L can go as low as 0. So that means N starts at 1. And if N is 1 bigger than L, then how many terms, yeah, what's the highest power you're going to have in your polynomial if N is 1 greater than L? So let's say N equals 3, L equals 2. Zero, that's right. So if N is only 1 bigger than L, you have just the constant term in your polynomial. If the difference between N and L is 2, then you have 2 terms of the polynomial. You have the constant and proportional to R. And then if the difference between N and L is 3, you'll have an additional term and so on. So N and L together tell you how many terms are going to be in your polynomial. Yeah, this is just a review of all of the craziness that we've done here. And so, once again, we rely on the math of others that are, let's just say, much more experienced mathematically than we are. So the radial solution has both N and L in it. It's not just a function of N, it's a function of N and L. And so it depends on this thing here. And I look at that and I'm like, what? Well, what that is the associated Laguerre polynomial, which comes from the Laguerre polynomial. And just like what you had for the homework where you did the using the Legendre polynomial and associated Legendre functions, you have the same type of thing here that you can build up what your radial solution is by first taking this to find your polynomial and then taking this associated function to find what you're going to put in here. And it's, as it looks, it's kind of ugly. So we're not going to sit and worry about that. We're just going to go now to our solution. We should have a combined wave function that has the angular portion times the radial portion. The angular portion had 2 pieces, the azimuthal term and the rest of, well, let's just look at this here. One's altitude and one azimuth, and this one is the one that's based on the altitude. And this R is this crazy long function. And so if you want the complete function, what do you have to do? Multiply them together. And notice we've got lots of exponentials in here to make life fun. You multiply them together and you get an ugly function. Now I want to look at, for the rest of our time period, this website, which of course I don't have open, the Orbitron. Have you guys ever looked at the Orbitron? No. Well, you should. So I had this open for class yesterday, but of course I didn't get it open for class today because I forgot. This here is a website that shows us what the outcome is of the calculations that we have just finished doing / perusing. So it shows us, for instance, the 1s orbital. What can you tell me about a 1s orbital based on the quantum physics we've just done? What does S mean? If it's not coming to you, that's fine. What quantum numbers have we learned so far? N, L, and M. N is our principal quantum number. And it tells us energy primarily. So it's the thing that gives us the energy. Then we have L. L is our, I'm going to call it angular momentum. You'll see different names for these. It's our angular momentum quantum number because it tells us our angular momentum. I'm just going to put L squared because, well, L, same difference. It tells us the angular momentum. And then M is the one that tells us the orientation of angular momentum, L sub z. Now, you'll find different names for these, and I'm not worried about the different names. What I am concerned about is what they tell us. And so we talk about shells and subshells. And so the N is telling us the shell. And the L is telling us the orbital. And the L sub z is telling us which variation of the orbital.
And just so I get this straight, did we define that L had to be greater than 0, or could it be equal to 0?
Okay, so rules we had were N has to be an integer that's greater than 1. Because if L is 0, N had to be 1. L is an integer up to N minus 1. And then M, or as we'll learn to call M subscript L, is from minus L to L. So now these L's, the actual names for the orbitals come from meanings that come from spectroscopy. People looked at the spectra and said, oh, if it has this orbital, it looks like this. And I don't remember them, but I know that they come from them, and I remember what the first one is. So if L is equal to 0, that's an S orbital. So S means L equals 0. Identical. They're just different way of saying it. And that stands for sharp, because you had sharp peaks. Remember in class of physics when we used the glasses and we looked at the lines? Those lines were sharp. Then we have, if L is equal to 1, that's a P, and I don't remember what P stands for. If L is equal to 2, that's a D, and that stands for diffuse, pretty sure. And then if L is equal to 3, SPDF, and boy, that can't be fine. 4 is G, and then it goes on like that, except for we skip one. I don't remember if it's I or H that gets skipped, but we skip one in the numbering, but the letters go alphabetically after that. So SPDFG, and like I said, it's either H or I that gets skipped. So if we look at Orbitron here, it lists a 1s. So what does the 1 mean in 1s? Okay, so n equals 1. The shell is 1. And what does the s mean? L equals 0. And so if I click on this 1s, it's going to show us some, sorry, you need Macromedia Flash to use Orbitron. It worked last year. Well, that's disappointing. That's extremely disappointing because that's what I have for the rest of the class period. Let me actually see if it works on. Well, that's coming up. Let's try
Is it blocked on there? Did you try to...
Yeah, that's not working either on Edge. So maybe I have something. Yeah, maybe. I mean, obviously I don't have the right thing installed there. Okay, so just changing over. So you're not going to see any of this stuff on. They're probably like, well, you know, that's really not exciting. Here's a bug that we don't know about in Chrome. You know how we like to zoom in or out? You cannot do that in the first tab. But if I copy this and go to any other tab, then I can zoom in or out. See? Just, you know, a little trick that I learned as I got frustrated trying to do grading stuff. So that's what S orbital looks like. What is this representing? Right, you've seen these a lot. So that's why I'm asking the question rather than just telling you. Yes, this is the region where you have a high probability of finding electrons. So the way this is determined is somebody says, okay, in what region do I have like a 97% probability that I'll find the electron? And we draw that. So different people will choose a different percentage and get something that looks slightly different. So here's the wave function. Oh. Here's the wave function. Like, why didn't it work? So that wave function is just pretty boring, right? What do we see here? It says psi. It's dropping off as we go away from R. This is showing the electron density, psi mod squared. Remember, psi mod squared is telling us about the probability of us finding it. And one might say, aha, where are we most likely to find the electron? What would you say just looking at this picture?
R equals 0.
Yeah, R equals 0 at the nucleus. But that's not the answer. Why is that not the answer? Because we have a spherical distribution. How much volume do you have at R equals 0? 0. And so we have to take this and multiply it by dV. The probability of finding it at some location is multiplied by dV. So here we have the dV, which is 4 pi r squared is the area, and then you'd have dx. And so here's what you get when you take your wave function, multiply it, well, wave function mod squared, doesn't show the mod here, times the 4 pi r squared. And now you can say, aha, where am I most likely to find the electron? At the highest point, right? And it turns out that what you get here is exactly the same as the Bohr radius, based on what we've done so far. And so the most likely place to find the electron is at the Bohr radius. But you certainly could find it well beyond the Bohr radius. In fact, in theory, you can find it infinitely far away, right? It's asymptotically approaching 0, not identically 0. You don't expect to have an atom in your body with an electron that's outside of this classroom because it's really close to 0 probability. But theoretically, that could happen. And then it shows you the equations that go into this. So you can see, what is this y here? Why, that's a spherical harmonic. It says 1s, you know, that's specifying it a little differently. So let's go to, what would 2s mean, a 2s orbital? N equals 2, L equals 0. Given that, what is J? Maximum. What's the maximum J then? 1. Right? The equation that we had was that n is equal to J max plus L plus 1. So if you solve it for J max is equal to n minus L minus 1.
So the definition of L can only go up to n minus 1. We don't get that from that recursive relationship.
No, we did. That was the result of that definition that n equals J max plus L plus 1. Remember I said the smallest amount that J max can get is 0.
Oh, so if it is 0, then
and if J max is 0 and L is 0, then n has to be 1. And there's always going to have to be at least one higher than L. Okay, so this is going to have J max is 1, which means it has 2 terms in the polynomial, a constant and a linear one. So it's going to look different because of that. So here's the 2s orbital. Now, if you look at this, it has a blue region and a red region. What do you suppose the difference is in the blue region and the red region?
One has a higher probability than the other.
One does have a higher probability than the other, yes. One of them is where psi was a positive value, and one's where psi was a negative value. So if we look at the wave function here, the wave function now has a positive region and a negative region. And if we look at the electron density, well, that's kind of what you expect. Not much chance of the electron being anywhere but the center, it would appear, except for you have to multiply by that 4 pi r squared. And now you have here is the place where you can have the most likely find the electron. But there's a secondary peak over here. And I'll skip the equations. What about a 2p? What are the quantum numbers for a 2p?
N equals 2, L equals 1, and can either equal 0 or -1.
Okay. And what about J max? 0. Okay, so that means that if I look at the 2p, it's okay, there's the dumbbell shape. And that dumbbell shape looks a little different than what I'm used to seeing because they chose a different probability limit. And the wave function, well, that looks almost exactly, not quite the same as what we saw before. So we have the 2 peaks. You can see now the 2 peaks. One of them is a positive wave function. One's a negative wave function. And the radial distribution, that looks just like what we had for the 1s. Now, the peak is not going to be the same place, but it still looks the same, fundamentally. Because J max was 0, just like the 1s had J max is 0. So let's go to a 3D. What is my radial distribution going to look like for a 3D? But let's start with what are the quantum numbers for a 3D?
L equals 2.
L equals SPD, yep.
N equals 3.
N equals 3.
So J max equals 0.
So J max is 0. Right, each one of these, the farthest one to the right is the J max equals 0. Well, up until coming up. Well, it does end quickly. So here's what that one looks like. It's a little more compressed, but it's still fundamentally the same. But if you look at the p orbitals, or the d orbital, excuse me, the d orbital has 2 distinct shapes. It has this one here, and then these here that are fundamentally the same shape, but oriented on different axes. So to me, that one's really weird. That's different, right? Because, general chemistry and organic chemistry, that's the highest chemistry that I've actually taken. And in those classes, we talk about the bonds you have with s orbitals, the bonds you have with p orbitals. We don't really talk about the d orbitals much. We do talk about sp hybridizations and that kind of thing. And then I look at this and I'm like, that's a little confusing. Well, now we just go on for fun. So the 3p is a more interesting variation of the P, right? It's got a second lobe in there. And the 3s, it now has more regions. Go to the 4s, even more. 4p, it's looking more cool. The 4d, yeah, you can see how it's related to the 3d, but it's got another lobe in there, or another smaller one. And then the 4f, whoever deals with these f orbitals, I don't know, but that's really cool. And I wish he had all of the backgrounds black like this because I can see it better than I could the others. And here you have 3 orientations for this form and then 4 orientations for this form. And what's different between those? The M's. The M is what identifies the difference in these. Now this does go on. G, who knows what a G orbital looks like? Well, you do now. These are what the G's look like. Good to know, right? I had a student once, these don't exist in real life. Why are we even learning about them? Well, kind of true. If you look at the periodic table, how much are we filling in the periodic table? Just to make sure we're clear, this is filling S's. And then we filled in 2 S's, and then we filled in P's. 3S1, 3S2, 3P, 1, 2, 3, 4, 5, 6. 4S1, 4S2, 3D. Notice we didn't put the 3D up here. That tells you right away there's something wrong with our results so far. Because the electron should be going into the lowest available state every time. And so what this is saying is that a 3D orbital is a lower energy state, or excuse me, higher energy state than a 4s. And so there's got to be more than what we've learned so far. So we keep going on. These are the P's, or excuse me, D's. These are the F's. The F's are the highest orbitals that we fill in our periodic table. So where does G come into play? Not theoretical. Excited states. Excited states are going to be using these higher ones. Now, as you can see, it's time for me to start my lab. But I do encourage you to spend some time looking at here. Like if you ever wondered, what does the SP3 actually look like? What's the wave function look like for the SP3s and so on? You can look at the hybridization. It also shows you examples of an anti-bonding relationship versus a bonding relationship, so that it's a sigma pi and a sigma. And likewise, you can look at pi, or a sigma star and sigma. You can look at pi bonds and so on. So it's a really cool website. Strongly encourage you to enjoy it.